In this video, I'm going to be going through probability for grade 11 level, specifically focusing on tree diagrams as well as contingency tables. So tree diagrams. In tree diagrams, each branch represents a probability of an event happening. So for example, if we flip a coin, we can get a heads or a tails. So we start there and we build a branch. So we have a head or a tail. And in tree diagrams, we also put the probability on that branch. So the probability of getting a heads on a coin toss is a half, and likewise a half for the tails as well. If we then had to do this again and flip the coin again, we would then have the same case, a heads or a tails. And then we do it for the other branch as well, a heads or a tails. So that would be a half, a half, a half, and a half. And what we can do as well is provide the different outcomes as well. So when we're working along a branch, what we do is we times together. So if the probability of getting two heads in a row would be a half times a half, because we're going our half plus the next part, which is a half. And because we're on the same branch, meaning we're going like this, we're going along one branch or one path, we times together. So that would be a half times a half, which is equal to a quarter. And that would be the case for all of these, because all of these events have the same probability. When we use multiple branches, then we would add the different branches together. So if we wanted to look at these three branches, or three outcomes of heads, 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 tails, and tails, heads, we would then add these three together. So a fourth plus a fourth plus a fourth would equal 3 over 4. So that's basically how tree diagrams work. But you need to be on the lookout for replacement or non-replacement. So if something is not replaced, so this is not for coin flips, because coin flips the probability will always remain the same. It's if you have something like a bag of marbles, and in the bag are red marbles and blue marbles. And if you take a marble out and you don't replace it, what happens is the next branch is going to have one less of that particular marble, as well as one less total marble within the bag. Okay, so if there's replacement, it means the probabilities will stay the same throughout the branches. But if there is non-replacement, it means that piece has been removed and it cannot be part of the next event, right? So you need to look out for that. So if something is not replaced, the denominator of the probability drops by 1 because there's less in that bag, and the relevant numerator drops by 1 because if you've removed one red marble, there's going to be one red marble in the next time you draw a marble from the bag. As I've said, when working on single branches, meaning, I'll show you this perhaps, meaning along one route, we use multiplication. But when we're working along multiple branches, then we use addition, like I said. So if we're working with those three, like I said, what we do is we use firstly that multiplication to get that specific root, and then we add all of those different roots together rather than timesing the roots together. So let's do an example of a tree diagram. In a communal fruit bowl in an office, there are 4 apples and 3 bananas. A fruit is chosen at random and eaten by a worker. Then another fruit is chosen and eaten at random by them. Draw a tree diagram to represent this information along with the probabilities. So the first 2 branches would be apple and banana. And the probabilities of those two, in total we have 4 apples and 3 bananas, so that's 7 in total. So the denominator is 7 for both. And in the beginning there would be 4 apples, so there's a 4 out of 7 chance of getting an apple, and for bananas 3 out of 7. And then they choose another fruit after they've eaten a fruit. So this would mean there's non-replacement because the fruit has been eaten. He can't put the fruit back that he's already eaten. So then we have an apple or banana again for both of them. But then the probability changes, right? Now there's only 6 fruit in each bowl, or in the bowl. So the denominator has to be 6. But then let's think about what the numerators will be. For the apple one at the top, there's 1 less apple if he chose the apple first. So there would only be 3 out of 6 fruit left. In terms of apple, 3 apples out of 6 fruit. Next would be the banana. The banana would stay the same because he chose an apple on that second branch. So we would still have 3 bananas. Next would be he's chosen a banana first and then he has an apple. So the apples would remain the same. So it would be 4 over 6. For the last one, he chose a banana first, so there were 3 bananas. Now there's 1 less banana because he ate that one, so there would be 2 out of 6. So your outcomes, or your possible outcomes, would be apple, 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 banana, banana, apple, and banana, banana. And the probabilities for those would be 4 over 7 times 3 over 6. The next one is 4 over 7 times 3 over 6 as well. Next would be 3 over 7 times 4 over 6. And the last one would be 3 over 7 times 2 over 6. And then you could work out these different ones, which would be 2 over 7. This next one would also be 2 over 7. And the third one. And the fourth one would be 1 over 7. A nice check to do that you can see that things are correct is that the numerator should all add up to the denominator. So 2 plus 2 plus 2 is 6, plus 1 is 7. So that looks right. So then let's get into the other questions. What is the probability of a worker choosing a banana, then an apple? So let's look at that. So that would be over here, a banana, and then an apple. So that would be this branch, this third branch here, 2 over 7. So it would be first 3 over 7, a banana, then an apple, 4 over 6, which equals 2 over 7. So what we've done there is we've only followed one route, so we're working along one branch, so that's why we are multiplying them together. Okay. Next is, what is the probability of the worker choosing 2 of the same fruit? So there's 2 different options here, right? If he chooses apple and apple, he's getting the same fruit. And if he chooses banana, banana, he's getting the same fruit. So now we are working with 2 branches. So we do the first branch, which is apple, apple, which is 4 over 7 times 3 over 6. But then we're going to add the other branch in as well. And that branch is 3 over 7 times 2 over 6 for banana, banana. So that means we have 2 over 7 plus 1 over 7, which equals to 3 over 7. Okay. Let's try another tree diagram question. There are 2 doors in a passage, door A and door B. Behind door A are 3 blue boxes and 2 pink boxes. Behind door B are 5 blue boxes and 4 pink boxes. A door is first chosen at random, then a box behind that door. Draw a tree diagram to represent this information. Okay, so first we're choosing a door, and there's 2 doors, which is door A and door B. And the chance of choosing 2 of those, or either of those, would be a half. It's 50-50 chance. Next would be the box behind the door. So the boxes are blue and pink and blue and pink. But let's look at those specific probabilities. So behind door A are 3 blue boxes and 2 pink boxes. So there's 5 boxes in total. So the denominator is 5. But there are 3 blue boxes and 2 pink boxes. So 3 over 5 and 2 over 5. For the behind door B, we have 5 blue and 4 pink. So that's a total of 9. So the denominator is 9. For blue boxes, it's 5 over 9. And pink boxes, 4 over 9. So our different outcomes would then be door A and blue, or door A and pink, door B and blue, door B and pink, and the probabilities would be a half times 3 over 5, a half times 2 over 5, a half times 5 over 9, and a half times 4 over 9. And each of those would then equal to 3 over 10, 3 over 10 again, 5 over 18, and 2 over 9. Okay, now we're ready to answer the questions. What is the probability of getting a blue box? So the only way to get to a blue box is to first open a door. And the 2 that have blue boxes is this third one and this first one. So we have to take both of those branches, probabilities, and add them together. So that would be, for that first one, door A and the blue box is a half times 3 over 5, plus our next one, which is a half times 5 over 9, which would equal 3 over 10 plus 5 over 18, which equals 26 over 45. I hope that makes sense. Next, what is the probability of getting a pink box? So there's 2 ways we could do this. Because we've just worked out the probability of getting a blue box and the pink box is the only other option that's left, we can either go 1 minus 26 over 45, because we know that the total probability will be 1 of choosing anything at all. But then the probability of getting a pink box, which is the opposite of getting the blue box, would be 1 minus that probability of getting a blue box, which would be equal to 19 over 45. The other way of going about this would be to do it manually, where we then take the pink box option, which is 3 over 10, and we plus it to the other pink box, which is 2 over 9, which would give us 19 over 45 as well. Next is contingency tables. So these are useful tabulated representations of one factor against another, where each cell of the table represents the number of events within that specific subcategory, and this table also has totals. So if we wanted to map gender against favorite type of food, so let's divide it into 2 categories, which would be sweet and savory. And our genders would be, assuming 2 genders, male and female. So then our table would look like this. On the top we would have one of the categories, so let's say male and female, so our gender. And then on the side we would have our other categories, which would be food, which would be sweet and savory. And then what we also have are our totals. We have a column here as well for our totals. So let's make up values. So male, let's put 5 with sweet and 6 with savory. So the total males would be 11. For females, let's say 2 sweet and 7 savory. So total females would be 9. And then we work across as well. So the total sweet would be 7. And the total savory would be 13. And the total would be 20. So that's how your contingency table works. We have 2 different categories and subcategories of each. You might have 3 categories. You don't have to have 2 in each. You might have 3. You might have maybe even more, 4 against 2, or you can even have 4 against 4. It just depends. And then how this works in terms of probability, each of these cells represents the number of people within the category. So the probability of a female who chose sweet would be 2, because female and sweet, over the total, which is 20, which would be 1 over 10. So that's how they work basically. So let's then do an example. So on a flight, passengers could choose between a vegetarian snack and a chicken snack. The snacks selected by the passengers were recorded. The results are shown in the table below. So what we have is snack against gender. So we have male and female and vegetarian and chicken, and each of the cells represent that subcategory as well as the totals. So what is the probability that someone chose a vegetarian option? So that would be everyone who chose vegetarian, regardless of male or female. So the total vegetarian is 32 over our total, which is 150, and that simplifies to 16 over 75. So contingency tables are very useful when we're looking at probabilities of different categories and factors. What is the probability that someone chose chicken given that they must be a woman? Okay, so that's a particular kind of question. So that we're getting like a kind of limitation here in this question. They're saying that they must be a woman, so we can only focus on the female part of this table. So our total, our denominator is going to be 83. And then within that we look at how many women chose chicken, which is 63. So it's 63 over 83, which is its simplest form, and that's the answer. So when you get given that conditional probability, we have to go and isolate that they must be a woman. So you isolate just the woman, and then you look within that category which one they're looking for actually. Okay. The next question, was the choice of snack on this flight independent of gender? Motivate your answer with the necessary calculations. Okay, so what we have to do here is use the independent formula. So the independent formula is the probability of A and B is equal to the probability of A times the probability of B. So in this case, what we can do is we can pick either male or female and vegetarian or chicken, and we then test out this formula if it works. So I'm going to isolate it to males who chose vegetarian. Okay, so the one piece is going to be male, the other piece is going to be vegetarian. Okay, so the probability of male and vegetarian is equal to 12 over 150, which equals to 2 over 25. And then I'm going to do the probability of male times the probability of vegetarian. So the probability of male is 67. So that's the total number of males. So 67 over 150 times the probability of vegetarian, which is 32. So we have to look at the total. So 32 over 150. And that equals to 536 over 5625. So it's quite clear that these two sides do not equal, which then means that the choice of snack is not independent of gender. Snack and gender not independent Okay, so you could have done this another way as well. You could have chosen the female and chicken and done it that way, or female and vegetarian and done it that way, or male and chicken and done it that way. You just have to prove that they're either independent or that they're not independent based on that formula. Okay.